Well, hello. Today we're going to discuss LeChatelier's principle. LeChatelier's principle is a very important chemical principle. It deals with systems at equilibrium and how the systems respond to that stress to restore equilibrium. Now, for people, sometimes if we get stressed, we might eat too much or sleep too much or watch TV too much. These are ways that people deal with stress. Chemical systems don't do any of those things. So let's discuss what they actually do. Well, that'll wake you up, won't it? Well, we've got here a chicken that's telling us he wishes he has sweat glands. Now, I'm not exactly sure what that's about, but if you've ever been to a petting zoo and you've petted a chicken, they're not sweaty, even in the summertime. Or maybe you have a dog, a nice golden retriever, and you go out on a nice summer day and you throw sticks and the dog runs after the stick and brings it back, and you take the stick and throw it, the dog runs after it, comes back, and you say, "Good boy, good boy." Now, it doesn't matter that it's 100 degrees out. That dog will do whatever you want and it will not be sweaty. Now, what the dog is doing to cool itself is panting. And at the bottom of its pads on its feet are warm as the blood goes there to try to cool itself off. Chickens cool themselves in a similar manner. They pant and they put blood up to their little combs up here to cool off. So let's talk about eggs and eggshells for a minute. If you've done much cooking or baking, you realize that in the wintertime, when you break an egg, you have to really hit it hard to break the egg. It's very thick. In the summertime, the eggshells are much thinner. You barely tap them and they'll be cracking open. Now, this has everything to do with LeChatelier's principle. Here's a chemical reaction that says that an eggshell is made of the main component, calcium carbonate. Now, where does the chicken get the calcium carbonate to make the eggshell? Well, it combines calcium oxide and its food in carbon dioxide that's normally in its bloodstream. So using this synthesis reaction, carbon dioxide and calcium oxide produce the eggshell of calcium carbonate. Please notice that there is an equilibrium, a double arrow between the products and the reactants. That means this reaction can go in both directions. So as the temperature increases, the chickens have to pant more. What the effect of that is the amount of available CO2 is going to go down. It's going to decrease. As the amount of CO2 decreases, that means that's the limiting reactant. You're not going to be able to produce as much calcium carbonate. In other words, the system stresses, this stresses the system and shifts the equilibrium to the left. I guess it's not a male chicken, it must be a female. The effect of this is, though, the eggshell is going to be thin and fragile. Now that's a problem if you're an egg producer, because just the movement of the eggs can cause them to break. So we need to figure out a way to make those eggshells a little bit thicker. So here's our chemical reaction again. And we know that in the summertime, the concentration of CO2 in the chicken's blood is going to decrease due to panting. So the question I have, and what is the effect of that, of course, as the CO2 level goes down, the equilibrium will shift from the product of calcium carbonate over to the reactants to try to increase the level of CO2. So again, if this is the eggshell, calcium carbonate, and this is calcium and oxide plus carbon dioxide, as this level goes down, it's not balanced, it's not at equilibrium. So what happens is the eggshell goes down, breaks down, bringing back the CaO and CO2 to a new equilibrium. Now, some students think that equilibrium means equal rates. Now, that's not necessarily correct. Let's pretend you're on a treadmill. If you're walking on a treadmill, you can turn the treadmill up, but you have to walk faster, or you can turn it down and you can walk slower. You're still at equilibrium in both cases. The key is the pace that you're walking has to be the same as the pace that the treadmill's turning. So equilibrium can be achieved at different conditions. So let's get back to this question. You're now a chicken farmer, and you are trying to figure out how to get those eggshells thicker. So what could we do? Let's think about that for a second. Oh, Prapul, you have an idea. What is it? Prapul says air condition the chicken house. Okay, stop laughing, everyone. Stop laughing. Can somebody tell Prapul what's wrong with that idea? Oh, it costs too much money. You see, eggs don't cost very much money. You can get a dozen eggs for $1, $1.50. And if you have to air condition a chicken house, that's going to cost a lot more money to keep those chickens cool. So that's not a good idea. What else could we do? Oh, you have another idea, Prapul? Pump carbon dioxide gas into the chicken house. Yeah, that would be a good idea if we were trying to raise and then kill the chickens. You see, chickens die if they inhale too much carbon dioxide, so that won't work either. We need to come up with another idea. I have one. What if we give the chickens carbonated water? Now, what I mean by this is we're going to give them water. When it's hot, they're going to drink more, but we're going to carbonate the water. By doing this, the chickens will be drinking in the carbon dioxide gas that they need, that they're replacing whatever they need that they've been exhaling out. And this is actually what the chicken farmers do, is they give them carbonated water in the summertime to make their eggshells a little bit thicker. So let's think about this. If the concentration of the carbon dioxide increases, so CO2 increases, so here we have the calcium oxide and carbon dioxide, here we have the eggshell. If the carbon dioxide level goes up, then what that's going to do is cause the eggshells to have to get thicker to restore the equilibrium. So it's going to shift the equilibrium as the carbon dioxide goes up to the right toward the calcium carbonate to make those shells thicker. Excellent, excellent thinking on that, guys. The other thing that farmer may do is add a little bit of extra food with calcium oxide to increase the concentration to make those eggshells a little thicker when it gets too hot. If you increase the concentration of calcium oxide, it's going to stress the system and shift the equilibrium to the right to make the eggshell a little bit thicker. All right, well, let's do another example of LeChatelier's principle. This is called the Haber process. This is a very important reaction in which nitrogen gas and hydrogen gas combine to make ammonia. It is an exothermic reaction. Why is this reaction important? Well, ammonia is used to make fertilizer as well as explosives. In World War II, Germany was fighting on many fronts and was running out of explosives. So they needed to figure out a way to get more ammonia to make more bombs. And Fritz Haber, a German scientist, realized or figured out that you could do that. You could make ammonia synthetically, because up to that point, they would have to go and get ammonia. They didn't actually get ammonia. They got other chemicals, and they got them from South America. And the U.S. put an embargo around South America, making it basically impossible for them to get the materials they needed. So the chemists figured out that you could make this by combining nitrogen and hydrogen under the right conditions, and that made World War II go quite a bit longer. Let's look at what happens here. If you raise the temperature, if you heat this reaction up, by increasing the temperature, you stress the system, you have too much heat, and that's going to shift the equilibrium over toward the reactants and slow it down. So this you would not want to do at high temperature. Instead, you want to do this at a very cold temperature, and that would cause the greater production of ammonia. So we don't want to raise the temperature, we want to cool the temperature for this reaction. The next thing we could consider is increasing the pressure. Now this is a harder one to explain, but I think we can do it. If we notice we have 1 mole of gas, nitrogen here, 3 moles of gas here. So we have 4 moles of gas on the reactant side and only 2 moles on the product side. Now let's humanize this for a second. Let's say we have 2 families. One family has 4 family members, one has 2 family members. And for some reason, they both have to downsize and move to smaller homes. So both families, my family of 4 and my family of 2, have to move into very small apartments. Now, which family do you think is going to feel more stressed, the family of 4 or the family of 2? Well, of course, the family of 2. And the same problem is going to happen here. When we increase the pressure, we actually confine the gases, giving them a smaller space. So what that means is my family of 2, my 2 gases can handle that stress better than my family of 4, my 4 moles of gas. So the family of 4 feels more stress, and to relieve the stress, shifts from the reactant side over toward the product side. So increasing the pressure would favor the forward reaction in which 4 moles of gas converts to 2. If you decrease the pressure, it would cause the equilibrium to shift to the left. Now, what would be the effect if you had 3 moles of gas on the reactant side, 3 moles of gas on the product side, and you altered the pressure? If you said no shift, you are correct. If you have the same number of moles of gas on both sides, there is no shift in the equilibrium. Finally, let's look at the effect of decreasing concentration. If you were to remove ammonia from the system, then the system would be looking for the ammonia. It's not there, and keep making more and more and more. So if we can figure out a way to remove the ammonia, we can cause this reaction to favor the production of ammonia. And that might be simply you make a system where you have a valve where you can open it up, so as the ammonia is formed as a gas, you cool it off and it liquefies, and then you open a valve and it can be removed from the system, and you can keep pumping in nitrogen and hydrogen, getting it under the right pressure to form ammonia, cool it off, turn it to a liquid, and continually drain it. And this is the process that ammonia is made even to this day. We could write an equilibrium expression for this. Remember before we had an equilibrium expression of Ka for weak acid? Well, we can do the same thing, an equilibrium expression for this chemical reaction. So let's look at it here. So the KEQ, equilibrium expression, is always equal to the concentration, that's what brackets mean, of the products divided by the reactants. Now, we don't need to include heat, but the products in this case is ammonia, so it's the concentration of ammonia divided by the reactants, the concentration of nitrogen and hydrogen, nitrogen and hydrogen. Now, I did add a coefficient here. Where do you think this superscript 2 and superscript 3 came from? I'll give you a hint. Look at the chemical equation. Ah, good. You realize that whatever the concentration of the ammonia is, you have to square that concentration because that's the coefficient 2. Whatever the concentration of the hydrogen is, you cube that because it has a coefficient 3. This is how you write its equilibrium expression. Now, I'm not going to ask you to write equilibrium expressions, but I do want you to consider for just a moment what the numerical value of the equilibrium expression means. If you have a large value of KEQ, that would mean you have a lot of product, a big number on top, and a small number on the bottom. So a big KEQ favors the product. If you have a small numerical KEQ value, it must mean you have very little product, a small number on the top, and a big number on the bottom, meaning most things stay reactants. Small number divided by a big number is a very small number. So that if KEQ is small, it means the reaction is favoring the reactants and not breaking down very much. Let me give you another example, a couple more examples of LeChatelier's principle. So reversible reactions, just to kind of give you the background there, the reactants turn into products and products turn into reactants. And both of these can happen simultaneously. Ka, or acid dissociation, is a reversible reaction. So let's look at this example here of sulfuric acid. Sulfuric acid is a diprotic acid. It can give 2 protons and a sulfate. But really this happens in a slower process. And we won't go into that right now. I'm going to skip this on equilibrium and just mention that even though reactants turn into products and products turn into reactants, it might look like nothing's happening. However, the system is dynamic, not static. It's moving. It's like my hometown. It has a population of 10,000 people. Now, people are born there, people move in, people move out, people die. But basically, the population is steady at 10,000 people. So to the Census Bureau, it looks as though nothing's happening in that town. But I can assure you, life moves on and stuff does happen there. All right, let's look at LeChatelier's principle one more time. And there's our definition of LeChatelier's principle. When a system at equilibrium is disturbed, it shifts to a new equilibrium that counteracts the disturbance. So here we have the Haber process, the formation of ammonia. So I've got different disturbances and different shifts. So what I want you to do is, when I give you the disturbance, I want you to either point toward the reactants or point toward the products to tell me which way the equilibrium will shift. So if you increase the concentration of ammonia, which way will it shift? Good. You're telling me it's going to point toward the ammonia. As we increase the concentration of ammonia, it's going to shift the equilibrium to make more ammonia. What happens if we add more hydrogen? Well, if you add more hydrogen, it's going to shift the equilibrium to make more ammonia. Very good. What if you add more ammonia? Good. I couldn't fool you, could I? If you add more ammonia, it's going to shift the equilibrium in the opposite direction and actually slow down this chemical reaction. What happens if you remove ammonia? You got it. It's going to make more ammonia. What if you add a catalyst? We haven't discussed a catalyst for some time. What does a catalyst do? Right. A catalyst speeds up a reaction. So which way is it going to shift the equilibrium? To the right? Toward more ammonia? No, that's not going to happen. The equilibrium is not going to shift. Now, this is an important idea to figure out. If we think about, if we're driving from Bloomington Normal to Peoria, it's about a 30-mile drive. Now, if I go 70 miles an hour or 20 miles an hour to get to Peoria, it might take me longer to get to my final destination, but the distance between Bloomington Normal and Peoria doesn't change. So when you add a catalyst, you simply get to your final destination faster, but it doesn't change the destination. So a catalyst lowers the activation energy, will get me to my final destination faster, but it doesn't actually shift the equilibrium. The equilibrium remains the same. That's a common question that students will tend to miss. Finally, if I increase the pressure, let's see if we remember, I have my family of 4, 1 mole of gas, 3 moles of gas, 4 moles of gas here, 2 moles of gas here. If I increase the pressure, they're moving to a smaller home. The family of 4 feels more stress. And to relieve that stress, it will shift over to the side of the ammonia. Excellent. Good job. I hope you're starting to understand LeChatelier's principle. Here's one more application of LeChatelier's principle. Some people have those glasses, when they hold them into the sun, they get dark. I'm not talking sunglasses, but like transition lenses is the name brand that they're usually sold as. So if we look at that, here's the chemical reaction. In between the glass, they've added a solution of silver chloride. And when you take your glasses outside, they receive more ultraviolet energy. And that causes an equilibrium to take place where the silver chloride, right now we're ions, Ag1 plus and CO1 minus, they end up forming the atoms silver and chlorine. Now, the 0 means no charge. This does not have a 1 plus charge or a 1 minus charge. There's been a transfer of electrons. And when electrons are transferred, that has something to do with light. So, just as point of reference, when you're inside, the glasses are clear. When you go outside, your glasses absorb energy. They darken. So when you go outside, what happens is there's more intense sunlight. So that means the energy goes up on the reactant side. As the energy goes up, what that's going to do is shift the equilibrium from the left, from the reactants, over to the right. So as it shifts the equilibrium to the right, the glasses are going to darken. That's what you want to have happen. Then what happens is, as you go inside, it looks as though everything is getting dark. Everything's not dark. Your glasses are simply dark, letting less light get to your eyes. So now there's lower energy inside. As there's less energy, that stresses the system, and the system will respond by making the dark glasses go from the right side of the equation over to the left, from right to left. And what that means is, as it shifts from right to left, there's going to be a new equilibrium where the glasses lighten. And this is how light darkening glasses operate. It's based on LeChatelier's principle. I wrote some stuff here. I'm not going to read it to you. You feel free and pause the video if you want to read about how those glasses work. I'm not going to ask you in my class the chemical reactions of how that all works. The last thing I want to talk about was how we maintain blood pH. And that's amazing to me, that if we took blood samples from any one of us, our blood would have the very narrow range, pH is 7.2 to 7.4. In fact, if you fall out of that range, you're going to have some very serious medical conditions. Now, it always amazes me that a pregnant woman can have cravings for pickles and maybe eat a bunch of pickles and even drink pickle juice, which is very, very acidic, yet her blood pH doesn't change very much. So how is that? What's going on in our bodies to maintain blood pH? Well, I've added the chemical reaction at the bottom that makes this happen. So you recognize, I hope, H plus as the shorthand version of acid. So we have an ion in our body called the bicarbonate ion, this one right here. Now where you get the bicarbonate ion is from bread, eating carbs. And as long as you're eating a normal diet, you're not going to have a problem maintaining your blood pH. Now if you go on a diet like the Atkins diet that tells you not to eat any bread, then you might have a problem because you're not going to have enough bicarbonate ion to maintain your blood chemistry. And that's why it always says contact a doctor before starting any diet. So let's think about what happens. If we have enough bicarbonate ion in our bloodstream and we add a bunch of acid, the acid concentration is going to increase. It's going to combine with the bicarbonate ion, and there's an equilibrium. As the acid level goes up, it's going to shift the equilibrium over toward the right to make more carbonic acid. Now, carbonic acid is an acid that you're quite familiar with. If you're running, sometimes your muscles start to ache, and the way you get rid of that is you stop running and you start exhaling. And what you're really doing is causing this lactic acid to build up, and it stresses this system. And so as this goes up, you shift the equilibrium to the right and you exhale out water and CO2. So your body has cleverly taken the acid, combined it with bicarbonate ion, shifting the equilibrium to increase the concentration of lactic acid. As the lactic acid level goes up, your body then shifts that out of your body as water and CO2. So we sort of see a graphic. The little blue dots represent acid going into your bloodstream. That acid combines with the bicarbonate ion to make carbonic acid. Carbonic acid and lactic acid are isomers. They're mirror images. The lactic acid you're familiar with. The carbonic acid you're somewhat familiar with too. It's what's in carbonated beverages. So then that carbonic acid level increases and it shifts the equilibrium to the right as we exhale out water and CO2 gas. Now, the bicarbonate ion circulates, it's in your bloodstream all the time, and it's in equilibrium with the acid in your body and the base, the hydroxide. So in the lungs, the bicarbonate ion is going to combine with the acid, and it's going to then produce a water molecule and carbon dioxide to exhale. And this is how you maintain your blood pH. Now, your blood pH can actually get off. of what the normal, what it's supposed to be. If you become too excited, you start to hyperventilate. You're going to exhale out too much CO2 too quickly, and that's going to be a problem. Now, if this happens, it says it accelerates the degradation of carbonic acid being broken down. So what's happening is you're exhaling out too much CO2. This is leaving your body too rapidly. That means the concentration of CO2 is too low, and the carbonic acid is going to have to break down to try to make more. As the carbonic acid breaks down, then it lowers the level of carbonic acid, and then your body is going to attempt to make more carbonic acid by combining acid with the bicarbonate ion. The net effect of this is the amount of acid in your bloodstream is going to become too low. If you don't have enough acid, you have too much base. So your pH is going to be above 7.4 and be alkaline, and this condition is called alkalosis. The symptoms you're going to see are overexcitability or even death if not checked. So it's sort of like you go outside and there's a big hill and you start running down the hill and your little legs go faster and faster and faster and faster and you can't stop yourself. And finally, you stop and you roll down the hill. Well, the way you can stop this is you can simply breathe into a paper bag. If you breathe into a paper bag, you're going to be exhaling out carbon dioxide, increasing your level of carbon dioxide, and it's going to cause that overexcitability to settle down very, very quickly. Perhaps you're having difficulty sleeping at night. Simply pull the sheet over your head and you're going to inhale your own CO2 and it's going to calm you down. You're not going to die. You're going to get enough oxygen, but it will cause you to relax a little bit as well. Now, the reverse of this, acidosis, happens if your breathing becomes too slow. I'm thinking about if you visit a nursing home, sometimes the elderly people, they kind of breathe with their mouth open and very slow. Boy, I already feel calmed down from just breathing slow. What happens is if you breathe too slow, you're not exhaling enough CO2 out. So the CO2 level in your body builds up. As the CO2 in your body builds up, it stresses this equilibrium. Too much CO2 shifts the equilibrium to make more carbonic acid. As the carbonic acid level goes up, it shifts that equilibrium and it pushes it to make more acid in your bloodstream. The amount of acid increases, your blood pH becomes less than 7.2 in a condition that we call acidosis. Your blood becomes too acidic. Now, the way you fix this in a nursing home is you bring in exciting activities for the residents to do. You bring in bingo and they get excited, or whatever you want to do to get their blood pressure up. I even heard of one time where people brought in like strippers to get the elderly people a little bit more excited. I think that caused a great deal of controversy and is not generally the way they increase the breathing of the elderly. Okay, I think I've given you quite a few examples of LeChatelier's principle. We've talked about in your blood chemistry how you maintain blood pH. We discussed glasses that get darker or lighter depending on the amount of light they're exposed to. We talked about eggshells, lots of examples, and finally the Haber process to make ammonia. I hope you have a better idea what LeChatelier's principle is. I just want to give you a note to remind you that a catalyst does not change equilibrium. It only changes the rate at which you get to that equilibrium point. Take care. Have a good day. I'll talk to you later.